Hi, this is the last recording for the entire semester. This is for question number 5 of the final exam. So let's scroll all the way to the question itself. This is question number 5. And for this question, you have to remember how to take 2's complement because it states here pretty clearly that you have to do it by 2's complement. So let me just read the question first and see if there's anything to explain in the question itself. X underscore low is the label of the least significant byte of a signed 16-bit number, and let's call the number X, whereas X underscore high is the label of the most significant byte of the same signed 16-bit number. In the following area, write the assembly code to compute the arithmetic negation of the value X and store that back into the same 2 bytes. So the value X is a 16-bit number, or something that can be represented by a 16-bit signed number. This means that the 16-bit signed number if the 16-bit signed number represents negative 2600, the new value should represent positive 2600, and vice versa. Of course, your code must work with any signed 16-bit value except for negative 2 to the power 15, because the positive version of this value cannot be represented by a 16-bit signed number. Your code must use 2's complement as arithmetic negation. You are free to use any toy processor instruction register and labels. There is no need to preserve the flags register either. So it's all freeform as long as it works in the toy processor. You get full credit. Okay, so first let's review what is 2's complement. 2's complement value of some value X is basically the one's complement of the same thing plus 1. And 1's complement is bitwise not, so we have a bitwise not of X plus 1. So that's basically what we want to do with these 2 bytes. So the first thing we want to do in this particular program is to do a LDI A with X, because X low is the label, and we need to get it get the content. So also it doesn't really matter one way or another, but dealing with the high first is actually easier. So we'll take the negation first, and then the next thing we do is to do LD B from A, so that we can just keep using A as the address of this particular byte. And once we get the actual content of the most significant byte in this case, we can do a bitwise not. Okay, this is a bitwise not, and I'm just thinking about whether we have enough registers to do this or not. We may not have enough register to do this if I were to preserve the value of X underscore high. So I'm going to just not preserve that. So I'm going to load A with X underscore low, which is the least significant byte of the 6-bit number, and then do the same thing, except this time I will load it into register C. So now register C has the least significant byte of the 16-bit number, and then we'll do a bitwise not of C as well. So now we have the most significant byte bitwise not or negated and put into register B, and the bitwise not version of the least significant byte stored in C. So then the next thing we need to do is to add 1 to it. So we do LDI, once again we use A, register A, and then we just add 1 to the least significant byte first, which is stored in C. So we do this. Now this is the important part, because this can trigger a carry, which we then have to carry to the most significant byte. So this is how we have to be careful, because now we have to do LDIA with C1, which means C equals to 1. We put the label here. If we continue here, that means we are done, because there's no need to deal with the carry to the most significant byte, which means we can then jump to the end of this section of the code. So we'll say done here, and at this point we can say LDI A with done and JMP to A. When the carry is a 1, after adding 1 to the bitwise negated version of the least significant byte, then we'll have to make sure that we take this carry to the most significant byte. So now we need to do LDIA with 1, and just add it to the the most significant byte, which is stored in register B at this point. So we add A to B. So at this point, okay, when we get to the label done, then we'll be done with both the least significant byte and the most significant byte. So now all that is left to do is to store everything back into x underscore low and x underscore high. So then we just have to say LDIA with x underscore low. The order is not important at this point because we're just storing those 2 bytes back into memory. And we do a ST to wherever register A points to. And this is going to be the least significant byte, which is stored in C, register C. And then we'll do a LDIA x underscore high and STA, comma B, because register B has the most significant byte of the result. So this code should get everything done. So we'll go ahead and actually complete the program. Dot byte. Let's see. We'll try something that is negative. So x underscore high byte 255. So in this case, because the low byte has all the ones and the high byte also has all the ones, it is together we have 16 ones, which is representing the value of -1. The arithmetic negation of that should be just the positive 1, which is represented by a 1 in the least significant byte and a 0 in the most significant byte. So we'll go ahead and test this code to see whether it works or not. Okay, so we do Control C here. And then go to the assembler, go to my source tab, and paste it here. Check for syntax errors. There are none. And then we just get rid of some extra stuff that is not needed in this program. So get rid of all that. There we go. We go to the RAM file output, and everything looks good. And then we just have these 2 bytes representing a 1. So we'll go ahead and export this, or save as, download as, CSV. We'll store that, save it to temp/negate.ram. Okay, and then we switch to the emulator. As usual, we'll reset the processor first, and then we'll go ahead and store all that stuff. Load the RAM image. This is going to be negate.ram, and then we have the entire program. And we'll go ahead and do some logging. Okay, we're going to log those 2 byte locations. So let's go ahead and check out the actual location of those 2 bytes, which we can see in the assemble tab. So xlow is at location 25, which is a 19. So 19 and 20. 19 and 1A, sorry. 1A is the other location. So we go back here, and we go to the debug screen. Go to the RAM module and specify those locations. Oh, okay, this is all in decimal, so I didn't have to really go through the conversion, but that's okay. We'll just store these 2, into what we are looking for, and we can use the table here. Okay, it just looks kind of ugly right now, and we'll go start the simulation, and the program has now completed its execution. And let's go check out those 2 locations. We can kind of tell that it's not getting the... Oh, it is. So this is 19, it's a 01, and this is the other location. It's got a 00. So the program does work correctly, and so as far as I can see, it works okay. We can try something else. We can go ahead and try something other than these 2 particular values. Let me see how I want to do this. It's a bitwise not and the +1. We can always just use 0, 1, 0, 0, because that should negate back to FFFF. So let's try that. Before we do that, let's clock low, reset, load the whole program back in, and then just change those two locations. So let's go edit content, go to those locations, and put a 0 here, 0, 1 back here, and a 0, 0 here. So that way, when we're done with executing this program, these two locations should become FFFF, because that's representing -1, which is the arithmetic negation of just 1. Okay, so let's go ahead and start our simulation. That doesn't look good, actually. Let's find out. Yeah, I think it doesn't look good because somehow location 0 is changed to a 0, 0. It should not be a 0, 0. But that location is now FFFF. That is really weird. That should not be 0, 0 here. Why is it 0, 0? Let's go to the assembler and find out. It's an LDI instruction, and an LDI instruction is a 6C, not a 0, 0. When we look at the RAM file, it is a 6C1A, not a 0, 0. But let me just double check that I see something. Nope, it's a 0, 0. So something is not right. I mean, the program is overriding this location in the incorrect way. Let me just double check. So we'll reset again and load the program back in, and we'll also go to that location and change those bytes here. This is 28, 1819 and 20. See, these are the correct locations. So we have a 0, 1 here and a 0, 0 here. Close window and do our simulation. Text enabled, and sure enough, it is still incorrect. It is still storing a 0, 0 here. Oh, I know why. Because we never really put a halt instruction in the program, so it execute. Okay, let me show you what I mean by that. Let's switch back to the assembler. There we go. So we never put a halt instruction at the end of this program, right before x_low. So that means that right after the store into the most significant byte instruction, it continues to execute whatever is at the location of x_low as if it is an instruction, and then the next one as if it's an instruction 2. And the opcode of 255. Let's look up the instruction set itself. Let's see. So the opcode 255 turns out to map to a store instruction, one of the variants of a store, and I believe it is storing D to D, storing the value in register D to where D points to, and register D had not been used in this program, so it remained as a 0. So let me just double check that. Okay, so we go to processor and look up the assembler manual, because the opcodes are there. Or not. Let's see. Nope, not the opcode, but the assembler has the opcode for sure, because we can switch to the mnemonics tab. So right here we can see on this row, the ST, or the stored instruction, is starting with F0 as the base code, but it also takes on both registers. So when we specify register D, which is a 1-1 in binary, it has to go to bit 0-1 for register X. It also has to go to bit 2 and 3 for register Y. So when we specify the instruction FF, it is actually storing register D to wherever register D points to. And that's why it overwrote that location 0 with a 0. Okay, so now that it's explained, I feel much better. because I just hate programs to do whatever it's supposed to do correctly, but then it does something else that is not correct, which is dislocation. So if I had a halt instruction at the end of the code and before the declaration of the global variables, then we'll be fine. Okay, so that's good. So let me just switch back to the browser one more time, just so that we can look at the solution of this particular question. So as I said, having a halt instruction here is going to be good, but it was not requested in my instruction here, because the idea is I just need a chunk of code to do the arithmetic negation, and that may or may not be the entire program. So that's why I did not specify a halt instruction at the end of this particular sequence. If you have it, great. If you don't have it, I'm not going to take any points off. Alright, so that should conclude the discussion of all the answers to this test, final exam, that is. So I'm hoping that at least you know the correct answer in this case, or one of the correct answers, because obviously there are many ways to do this. Alright, so I'm gonna sign off now, and I'll let you guys enjoy your winter break.